Welcome back to The Explainer. Today, we're diving headfirst into the incredibly cool world of computer models and simulations. Basically, we're looking at how scientists and engineers use literal lines of code to decode our everyday reality. It's all about recreating the physical rules of our universe so we can peek into systems that are otherwise completely hidden from us. So let's just jump right in. Let's start off with a bit of a mind-bending question. How exactly do scientists solve mysteries when building a physical experiment is, well, totally impossible? I mean, we all intuitively get the idea of a scale model, right? Like building a tiny balsa wood bridge to test its strength. But what happens when the thing you're trying to study is completely out of your physical grasp?
That is exactly where computer models step in. They solve problems we simply can't test in real life. Think about processes that happen way too fast. If a mechanical engineer needs to figure out why a car door shatters in freezing temperatures instead of safely crumpling, they can't just crash hundreds of cars in the Arctic. They use a simulation. Or what about things that are agonizingly slow, like trying to predict how water will diffuse through a porous foundation over the next 5 years? Then you have things that are just way too big. We obviously can't recreate the sinking of the Titanic in a lab to figure out why the bow in the stern looks so radically different down on the ocean floor. And of course, some things are just plain dangerous, like tracing the exact forensic paths of bullets at a crime scene. The wild part is, we can even use these models to essentially manipulate time itself. Take the Great Sphinx in Egypt. If you look really closely, the base shows signs of what looks like water erosion. Which brings up a crazy question. Did the Egyptian desert actually see significant rainfall over 5,000 years ago? Now, obviously, we can't hop in a time machine, but by feeding erosion rates into a backward time simulation, scientists can basically run the clock in reverse to see exactly what that ancient climate might have looked like. So the best way to think about computer simulations is like the ultimate, completely impossible scientific sandbox. It's this incredible digital space that scales to literally any everyday problem you can think of. You can inject artificial forces, you can tweak material properties, or even exaggerate crazy weather events, all without the physical risk, the massive financial cost, or the sheer limitations of real-world trial and error. Let's look at how this sandbox actually plays out in the real world. A CEO can use a wind flow simulation to figure out exactly where to put snow fences around a new building, rather than just guessing and praying the doors don't get blocked in a blizzard. Or a city planner can use dynamical modeling to retime traffic lights and kill highway jams. They basically treat rush hour traffic like a giant resonating spring system, where the stoplights act like hands pushing a swing at the exact right moment to dampen the jam. And jumping from city streets back to ancient history, scientists can even use audio simulation programs to recreate the roar of a long-extinct crested dinosaur just by mapping the wave equations inside its fossilized skull cavity. How cool is that? And this scales all the way down to the microscopic level too. Consider molecular dynamics. If we look at tetracosine, which is a long hydrocarbon molecule, interacting with a graphite surface, physical tools like X-rays only give us static snapshots, but a simulation lets us watch things that are way too small to see with the naked eye actually in motion. We can watch the exact process as the temperature rises, the ends of the molecules physically flip up, the rows start shifting, and eventually the entire system melts right in front of us. Okay, but seeing all this incredible predictive power naturally brings up a pretty big question. How do we actually trust the matrix? How do scientists know their models aren't just spitting out total nonsense? Because think about it, if you accidentally reverse a single numerical sign in a heat transfer simulation, you might end up with hot boundaries actually cooling a system down. Or if you mess up the buoyant force, you'll get a wildly absurd world where helium balloons sink like stones. The answer to that is a super rigorous process called validation. Let's take a baseball flight model as an example. You don't just write all the code at once. First, you run a base model with 0 air and 0 gravity, just to make sure the core math works. Then you add gravity. You run it, you check it against reality. Okay, looking good. Then you add drag resistance. Check it again. Finally, you add the Magnus force from the ball spinning. If every single one of these added layers consistently checks out against known physics, well, then the model can finally be trusted to make predictions in totally uncharted territory. It really all boils down to balancing simplicity and complexity. It's the classic Goldilocks analogy. A model shouldn't be too simple. Like, if you're simulating a bullet hitting an arm, you absolutely cannot just model the arm as a solid cylinder with average properties. You have to account for the physical differences between muscle tissue and bone density, or you're missing the core physics entirely. But on the flip side, it shouldn't be so overly complicated that it just hogs computing power without adding any real value. It has to be just right.
Section 1. The Brass Origins of Computing.
To truly appreciate these modern digital marvels, we need to take a quick pivot and look at the highly surprising 19th century origins of all this. Long before electricity and silicon chips, the foundational ideas of computer simulation were already taking physical shape. Enter Charles Babbage's difference engine from the 1800s. Back then, astronomers needed crazy precise calculations to predict planetary positions. So Babbage designed this massive, hand-powered mechanical computer that used physical tumblers and cylinders to crank out complex trigonometric functions. The whole goal was just to remove fallible human error from the equation completely. But Babbage didn't stop there. He went on to theorize an even more advanced machine called the analytical engine. This thing was a beautiful brass and mahogany construction. It was a digital, mechanical computing device so profoundly ahead of its time, it essentially passed the Turing test a full century before modern computers were even a twinkle in anyone's eye. And here is where it gets really wild. There is a direct, perfect comparison between those 19th century mechanical parts and our modern computer architecture. It maps perfectly. Babbage's design had a component he called the mill, which functions exactly like a modern CPU's arithmetic logic unit. He had the store, which is exactly what we call RAM today. And every physical turn of the handle on his machine, that was literally the 19th century equivalent of a modern CPU clock cycle. The entire conceptual architecture was already right there. Of course, we absolutely cannot talk about Babbage without bringing up Ada Lovelace. In the early 1840s, she translated a memoir about the analytical engine, and she went ahead and added a completely new, complex algorithm for calculating Bernoulli numbers specifically for this machine. That brilliant move cemented her legacy as the very first computer programmer in history. And honestly, considering the intense focus required to write those algorithms, she was also very likely the originator of the coder's bottomless coffee habit. So, while the 1800s gave us numerical analysis, the very first true computer simulations were born out of absolute do-or-die necessity during World War II, deep inside the Manhattan Project. Scientists had to solve the dangerously complex neutron chain reaction. Think of a nuclear reaction like a scheme of doubling pennies every single day. 1 becomes 2, 2 becomes 4, and suddenly it is growing exponentially out of control. They couldn't test this physically without risking a global catastrophe. So, mathematicians John von Neumann and Stanislaw Ulam built a 12-particle Monte Carlo model to simulate neutron scattering. And boom, that was the exact moment modern computer simulation was born.
Section 2. The future limits of computing.
Since those early World War II days, we've obviously come an unimaginably long way. We've gone from massive, room-sized machines to the smartphones currently sitting in our pockets. But that brings us to a really fascinating frontier. Where do the absolute physical limits of our computing power actually lie? You've probably heard of Moore's Law. Back in 1965, Gordon Moore noticed that computing power, specifically measured by the number of transistors you can cram onto a CPU chip, basically doubles every 2 years. This kind of exponential growth is exactly what has driven the incredibly realistic physical modeling we rely on today, powering everything from global weather forecasting to the stunningly realistic light and water physics in your favorite video games. But here's the catch. Computing power cannot grow forever. We are eventually going to hit some uncompromising physical walls. As we make transistors smaller and smaller, we hit atomic sizes where the laws of classical physics just straight up break down. You get quantum tunneling, where electrons just jump barriers unpredictably. We are also bound by the ultimate speed limit of the universe itself, the speed of light, which strictly limits how fast data can travel across a chip. And finally, we have to contend with the literal physical mass of electrons. We simply can't shrink hardware infinitely. So what is that ultimate limit? Well, when physicists look at the purely idealistic considerations of the energy contained in a specific volume of matter, they estimate the absolute theoretical limit of computing is 10 to the 50th power operations per second. To put that massive scale into perspective, a standard modern processor today runs a few billion operations per second. 10 to the 50th is a number so staggeringly huge it genuinely strains human comprehension. Which leaves us with a final, pretty profound thought to wrap up this explainer. If today's computer models can accurately retime entire cities, predict microscopic molecular melting, and reconstruct the sinking of the Titanic, what impossible, universe-altering mysteries will we be able to solve when our machines finally hit the absolute boundaries of physics? Think about that for a while. Thanks for joining me on this explainer, and keep questioning everything.